Hello, my name is David Starr, and today we're going to be talking about the strategy pattern. Now, the strategy pattern is arguably one of the simpler design patterns we might encounter in the world of design patterns, and it's a great place to get started if you're just introducing yourself to this idea of common patterns of object-oriented software design. Now, the strategy pattern is also very practical. I find a lot of uses for it in day-to-day coding, and it can really help us clean up some of our existing designs. Let's jump right in by taking a look at an example of why we might want to use the strategy pattern. We'll start by taking a look at some example code. Our example code will be that of a shipping calculator. The idea here is that we have a customer who's maybe checking out on a website, and we need to calculate the cost of shipping their order to them. Now, that cost may vary depending on how the customer has chosen they want the package to arrive. The customer has the choice of choosing Federal Express or FedEx, UPS, or the United States Postal Service. And we're going to calculate a different cost depending on which carrier the customer's chosen during the checkout process. Okay, here we are in Visual Studio, and we're going to take a look at our sample implementation. We're going to drive our sample implementation through some unit tests that we've written over here. We could just as easily have used a command line utility. You know, we could have created a command line exe to run our little app, but we've got some unit tests here. Now, the intent is that when we're shipping via UPS, then our particular order is going to cost $4.25. When we're shipping via the United States Postal Service, it'll be $3. And when we're shipping via FedEx, it'll be $5. That's what our tests are showing us. Now, we can break apart the functionality of our shipping cost calculator. Our shipping cost calculator is this little class here, and we're going to new it up, and then we're going to provide to it an order. We get an order from this little mother class. This is just a helper within our test project. There's no black magic here. We'll jump in and take a look. All we're doing is we're creating an order, and an order has a shipping method. So in this instance, our order actually knows how it wants to be shipped, and we have a destination address and an origin address. Okay, so back over in our test, we're going to pass that order to our calculator services calculate shipping cost method. From that, we'll get the cost of our order, and then we'll assert that our cost is correct. Now, before we go too much further, we'll just go ahead and run all of our tests, and they do in fact pass. So we know that our algorithm is correct. And maybe that's no problem. Let's go down into the calculate shipping cost and take a look at how this particular method's implemented. What we'll find is that the calculate shipping cost method takes an order as its input, and this is very common syntax that we might find in code. We are going to switch on the shipping method of the order. So how does the order want to be shipped? And that could be either FedEx, UPS, or United States Postal Service. And one thing about using this technique is that it's very possible that we're going to get a shipping method passed in on this order that we're not actually coding for. And so in that instance, we go ahead and throw a new unknown order shipping method exception. So we've had to account for that possibility. Down here in our methods that actually do the calculation, you may imagine that in a production system, rather than just having a single one-line return, after all, not everything is going to cost $3. We're going to go out, make some service calls. We're probably going to calculate some things like the weight of the items in the order. I don't know, there are a lot of things that can go into calculating the actual cost of shipping. So this would likely be a very large algorithm, as would the one for UPS. We have a different algorithm for UPS and finally another one for FedEx. For the purposes of our example, let's just work with these hard-coded numbers, realizing that we'd probably have a much more complex algorithm for deriving each shipping cost. Now, what are some problems that we can note about this type of implementation? First of all, our order actually has to know what type of shipping our customer preferred. That's arguably not appropriate for an order to even know what type of shipping the customer wanted. Depends on the data model and the domain that you might be using. But one thing we can see is that when we add a new shipping method, let's say, for example, we want to ship with DHL and our company cuts a contract with DHL to do some shipping, we're going to have to open up this class and we're going to have to modify it. Now that sort of breaks the open close principle right away, because we're going to be modifying this calculate shipping cost method. The open close principle states that a class should be open for extension but closed for modification. And I would venture to say that adding another case statement here would be opening up this class for modification. And then finally, anytime we want to change any of these algorithms, we're going to need to open up this shipping cost calculator service class and ensure that our algorithm for, say, the postal service, if that's the one we're changing, doesn't impact the algorithm that we have for UPS and FedEx. We may very well have some shared state because of the mechanism we're using here. So there are some issues with this architecture, and it would be nice if we could calculate things independently of the shipping cost calculator service class. And that's where the strategy method comes in. Before just diving in and taking a swing at implementing this strategy pattern, let's take a look first at its intent. The intent of the strategy pattern is primarily to encapsulate a related, or we could say family, of algorithms such that they are callable through a common interface and may be used according to the appropriate situation. The idea here is that we're going to let our algorithms vary as independent classes so that they might evolve separately from the classes that actually invoke them through the interface. This allows our classes to maintain a single purpose. In the case of our shipping cost calculator, it's going to be responsible for taking an order, executing a calculation about that order, and returning the results. What we don't want is to bleed all of the concerns of UPS versus FedEx versus other shipping services into our shipping calculator. That would not allow our class to maintain a single purpose. And this nicely separates the calculation itself from the delivery of the calculation's results. Well, what are some flags we can look for that let us know the strategy pattern might be applicable to our situation? First of all, we've got switch statements. Anytime we see switch statements in a method that's trying to choose which calculation it should perform, that really should be a red flag to us. There is very likely a better object-oriented way of determining that logic than a switch statement. So switch statements are kind of a red flag. Also, we know that adding a new calculation, like one for DHL, will cause our class file to be modified. And we've already said that we want our open-close principle intact. So these are good indicators that we might want to look at an alternative. The alternative that we have implemented is an example that creates classes for each type of calculation we want to perform and uses a common interface for each one of those calculations so that they might be shared by the calculator class. Let's see how this looks in a classic UML model. Here in Visual Studio's UML Designer, we see a rather classic model or explanation of the strategy pattern in action. Here we have a context class. The context class is the class that we will ask to actually do the work. In its construction, it takes an instance, a concrete instance of a class that implements our strategy interface. Our strategy interface declares a method that will be the one called by the context class to actually perform the calculation we're interested in performing. Now we would call context.doSomething. Context.doSomething would then use the strategy that it was given on its constructor to call perform work on the concrete class. And in this case, we have two concrete implementations of our strategy interface. Now, how does that look given the domain that we're actually using here? We'll have a shipping cost calculator service. This will be our context. You can see on its constructor that it takes an I shipping cost strategy as a constructor argument. An I shipping cost strategy declares a calculate method. The calculate method wants an order to be passed in so that it can use the information in the order to calculate the shipping cost. Well, back over here on our shipping cost calculator service, we can see that the calculate shipping cost will then also take an order. And so within our calculate shipping cost method, we'll invoke our concrete classes calculate method. As you might expect in our code, we're going to create classes for each calculation that we want to perform. These are our strategies, and we'll use a common interface for each strategy so that we can invoke it through a reference to the strategy interface within our context class. Now again, we'll start back over in our test methods. We have a test method here that is going to new up our strategy class. This is our UPS shipping cost strategy, and it's going to pass it to the constructor of the shipping cost calculator service. We will then new up an order or somehow obtain an order that we're going to use during our calculation, and then we'll call shipping calculator service.calculate shipping cost passing that order. It's not really that different from what we saw before, with the exception that we're passing our strategy into the constructor. Really quickly, I'll go ahead and run all of our tests to ensure they pass. They do, and now we can drill down and take a look at what our shipping cost calculator service is doing. When we call its constructor, it's merely taking the strategy and holding it as a member field, and later using that strategy to perform the work of calculate shipping cost, so that it's merely returning the call to calculate on the strategy itself. Now we'll take a real quick look inside these various classes to see what they're doing. It's pretty simple. Here's our FedEx strategy. It's merely returning 5. You can again assume that this would be a fairly complicated algorithm that we might go through to determine our actual shipping costs. We're just returning a constant here of 5. And you'll see similar implementations in our UPS strategy and in our postal service strategy. But all of them implement the I shipping cost strategy interface, which defines for us the calculate method that takes an order as a parameter. Of course, that was taken as an input to the constructor for the shipping cost calculator service. And we'll see in a moment that there are some variations to how we might construct all of this, but we've achieved basic separation of concerns between our algorithm that does the calculation and the class that's going to provide the results. We've also eliminated the need for the unknown order shipping method. It's now going to be impossible basically to find ourselves in a state. See, we don't need it. We can compile without it. It's going to be impossible to find ourselves in a state where we're going to throw that exception, because in order to get a shipping cost calculator service, we're going to have to pass in the correct strategy in the first place. So we don't have any non-deterministic behavior here. Now that we've broken our class structure apart to take advantage of the strategy pattern, there are some consequences of our new design. For example, although we may have been taking advantage of some shared member state within our context class previously, now our strategies really have to be self-sustaining. So they can't use the local members of the containing class like maybe our methods did before we broke apart into separate class structures. Also, we get to write tests for our individual concrete strategies, meaning that we can build up a test harness, maybe through unit testing, specifically for our UPS tests, and another one specifically for our DHL tests. If we're testing our context class, these strategies can be mocked so that we can provide very deterministic behavior via a mocked strategy into our context class itself. Now that we're using interfaces to abstract away the strategy, that interface can be our mocking point. And finally, we can add a new strategy without any changes to our context class, or our shipping service in our case. Now, the use of strategy pattern is very widespread, and you'd be hard-pressed to find a code base that doesn't do something like this. However, there are some very common situations in which we'll find strategy pattern in .NET. Specifically, delegates in C# 3.5 and greater really are just the strategy pattern being implemented in a different way. We're going to take a look at how that works in just a moment. Also, it's a very common practice for people writing ASP.NET MVC to use the strategy pattern to inject services and repositories, things like that, into their MVC controllers. Those can then be mocked for unit testing. If your solution happens to use an inversion of control container like Unity or Structure Map, this can also be very beneficial. But as we've seen, you don't have to be using complex tooling and strategies like this in order to get some good advantage from the strategy pattern. Now, as we've mentioned, there are some other ways of dealing with the strategy pattern or setting it up and having a solution that's considered a strategy pattern. For example, we can use functions or delegates within .NET to push in our strategies, or we can even use property injection, or finally we can, instead of passing the strategy on a constructor, we can pass the strategy on the method call that we're making. Let's take a look in Visual Studio at how some of those alternative models might look. Here in Visual Studio we have another implementation of the strategy pattern that is in a different project. This one is strategy variation, and it does exactly what we've been doing so far, but it does so in a slightly different way. Up here at the top, I've declared three different funcs, three different delegates, if you will, that are implemented in three different ways, just sort of to highlight the fact that this can be done in three different ways in .NET. Here we have a FedEx strategy, the delegate for which is declared as a method, and here we have an anonymous delegate being declared for the UPS strategy, and an anonymous delegate declared through a lambda expression for the USPS strategy. They could all use the same technique or not. Here we have the order that we're going to be processing. We're going to process the same order 3 times, and here we are newing up our cost calculator service and passing in the FedEx strategy, and then we print out the results of doing the calculation. We then do exactly the same thing with the UPS strategy, and finally with the USPS or Postal Service strategy. So if we run that, we'll see that our strategies were run properly and each returned the expected result. FedEx was 5, UPS was 4, and Postal Service was $3.25. One thing that seems maybe a little bit inefficient here is that rather than passing in the strategy as part of the constructor, what if we created a constructor for our shipping cost calculator service that did not require the strategy to be passed in? Here we've got our new constructor there, and rather than holding on to our func as we were doing in our original implementation, we'll just take our func. Actually, let me just grab it up here. We'll just take our func on the call to the method, like so. And this lets us get rid of some code. So now our context class really is just a bare bones class, and we're going to pass our strategy in during the function call itself. So we can flip back over here, and rather than newing up multiple calculator services, we'll just use the same calculator service several times, and we'll pass the appropriate strategy for each one. So we'll pass FedEx strategy in here, we'll pass UPS strategy here, and we'll pass USPS strategy here, compile, do a quick run, and again, the strategies were executed properly. So what we've seen is that we can actually inject the strategy on the method call itself. It doesn't necessarily have to go in the constructor. That does happen to be the more classic implementation of the pattern, however. All right, we've seen several ways to implement the strategy pattern, and in its essence, what it helps us do is decouple a given algorithm or service implementation, something like that, from a class that's going to deliver back the results of that work being done. Lets us encapsulate algorithms into class structures so that they're independently testable, and that helps us keep the open-close principle in place on our parent context class, the one that's going to be using the strategy to do work. We know now that switch statements are often a red flag for us, telling us that maybe there's an opportunity here to use a strategy pattern. And the good news is this is a fairly simple pattern to master, and there are several techniques for doing so, for implementing the strategy pattern. We saw that we can do so with delegates in C# 3.5 and higher, and we can always use that classic implementation using interfaces. Thank you very much, and I hope to see you in class sometime soon.